What we want to take a look at now is more national sized electricity. So we're going to scale right up to millions of homes and businesses and millions of appliances all over the country. And when you start powering that many devices, you can't be using batteries because there aren't enough chemicals to do it with. Although, having said that, people like Elon Musk and others who are involved in the production of electric cars, every car is going to need a huge battery inside it. And then we're probably going to need to put some solar panels on our roofs and have a huge battery the size of a fridge in our garages that will store up the charge ready to give to our car later on. So in actual fact, in the last year or so, there has been a big move towards the development of battery technology. But at the moment, we don't have that. And we're going to talk today about what we do have, which is called mains electricity. And there are some significant differences between mains electricity and the kind that you get from a battery. And that's what we're going to talk about this afternoon. But I want you to hold in your head that the main reason for this is just a sense of scale. We can't use battery electricity to power the world. So the reason for mains electricity is a scale thing. We just need to make sure that we have enough energy and enough power for all of the devices on a national level. Okay, so on your screen in front of you, you should be able to see a slideshow that I'm going to work my way through. I'm going to try and get it done in around about 35-40 minutes, and then there'll be some tasks for you to do without me at the end of the lesson. So that's the plan. We'll see how we go. Let's make a start. Okay, let's talk about two different types of electricity then, the one from the batteries and the ones that we get out of the plug sockets. So the type of electricity that you get out of oh, by the way, before I get much further, some of these simulations, they don't work so well over a streaming video. So the PowerPoint is available on Google Classroom. So if you're finding that anything is jerking or sticking or anything like that, you can pull up the PowerPoint yourself and kind of click through independently on your own screen. Okay, so on your screen in front of you is the kind of electricity that comes out of a battery, and it's known as direct current, which is kind of an old-fashioned phrase, but it's getting you used to this idea that the current goes directly from one end of the power supply to the other terminal on the power supply. You can see a simulation of maybe a coulomb of electrons on the screen in front of you. And in a real wire, there'd be coulomb after coulomb after coulomb. So remember, a coulomb's a bag of charge, a group of electrons. So in a real wire, you'd have coulomb after coulomb after coulomb going past you. But I've just simulated one there just to let you focus on it and see that it's just going in a single direction. Those electrons are piled up on one terminal of the power supply by whatever's happening inside the power supply or the battery. And then when we connect a circuit to it, those electrons flow around the circuit in one direction, and then they arrive back at the other terminal of the power pack. And round and round and round they go directly from one terminal to the other terminal. It's often referred to as DC for shorthand. Okay, that's kind of electricity that comes out of a battery or the power supply that we had in class. What about mains? How is that different? So yeah, I don't know how clear this will be on the video, but hopefully you can see that these electrons are traveling in the same direction for a bit, and then they stop and they come back again, and then they stop and then they go back in the first direction again, and then they stop and then they reverse up again, back the way they came. Now the phrase alternating current is used to describe this because the direction of travel keeps alternating. Sometimes it's going forwards, sometimes it's going backwards. The reason that this occurs is because the mains electricity is being generated by a power station. You might remember studying power stations back in year 9, and we will study them again, in particular the generator bit of them, a little bit next year. But for now, what I'm hoping you remember is that power stations involve something spinning, be it a wind turbine or a water turbine or a steam turbine. There is something moving, like the tides or the wind, or the steam from coal boiling up water. Something is moving and it makes something spin. And the spinning motion is used by the electrical generator to create the electric current, which is then sent out through wires across the countryside. Now, you don't need at this point in time to focus very much on exactly how an electrical generator works, but just fix in your mind that there is a spinning motion involved. And as the generator spins and generates the electricity, as it kind of does half of its rotation, it causes the production of an electrical current that surges to the one terminal of the power supply ready to go around the wires in the country. But then when the generator returns to its original position by carrying out the second half of its rotation, it kind of yanks all the electrons back again and throws them onto the other terminal. It's much more like you kind of putting your hand in a bowl of water and wafting it left and right. Sometimes the water goes to the left, but then when your hand comes back, you waft the water back to the right again. Now, that's a really simplistic picture to have in your head, but I want you to just understand that we don't deliberately set out to make the electrons jiggle left, right, left, right, left, right. It's an accidental byproduct of how we are having to generate electricity on a massive scale so that there is enough of it to supply the entire country. Now, it is true, actually, that since the first generators were designed and manufactured, we learnt how to combat this issue and to use the technology. We can fit extra bits to a generator and we can force it into producing an electric current that is pretty much a direct current. So hands up, first of all, it is actually possible to avoid generating alternating current if you just make your generators a bit more complicated. However, it turns out that an alternating current can do one thing, just one thing that a direct current can't. And that one thing turned out to be really useful. And because it's so very useful, I'm going to do a whole lesson all on just that one thing in the near future. So just keep in your mind that alternating current is doing its thing, left, right, left, right, left, right, as an artifact of how we generate it at scale. We could bypass it, we could sort it out, but we've decided not to on purpose because actually we quite like that alternating current can do one thing that direct current can't, and we'll come back to that in a couple of lessons' time. You might be thinking to yourself, if you haven't fully understood the electricity work that we've been doing so far, that this is a bit of a problem. That because the electrons never go anywhere, how could they ever possibly deliver any energy for us? If you look at the nearest wire to you right now, any wire, the electric current that is in that wire isn't going anywhere, probably. It's just jiggling left, right, left, right, left, right, especially if it's something that's plugged in. Those electrons have probably been in that wire since the wire was manufactured. All the times you've used it, it's the same electrons jiggling about inside it, left, right, left, right, left, right. They never do what the wires in class do. When I asked you to make electric circuits in class, those electrons really do start at one, excuse me, one end of the wire and move to the other end of the wire. Not these. These just go left, right, left, right, left, right. But it's not a problem because remember, we steal the electricity from the electrons through collisions with the ions. As long as the electrons are moving and bumping into the ions in the wire, we can transfer energy, kinetic energy, from the electrons to the component. That's how the bulb gets hot and gives out its light. And that's very similar to how we can make motors spin, speakers make sound. It's all about the electrons interacting with the ions that they're passing through. Generally speaking, as long as they're moving, we can take their energy. And it doesn't matter if they're moving in the same direction or if they keep reversing their direction. It doesn't matter as long as they are moving. So in terms of plugging stuff into an electrical current, generally speaking, it doesn't matter whether it's a direct current or an alternating current. Either way, as long as those electrons are moving, as long as there is a current of any variety, we can transfer the energy, the kinetic energy from the electrons. Some electronic components, like the LDRs and the LEDs that we were talking about, they do object to the electricity flowing in the wrong direction. So you have to be a little bit careful about some of those. And certainly plugging an alternating current into your phone would probably be a bad idea, and the charger you've got alters it to turn it back into direct current. But generally speaking, most things that we plug in, they don't really mind whether it's DC or AC. As long as the electrons are moving, we can steal the energy. So that's your first difference. The first thing that is not the same between the current from a battery and the current from the mains electricity. Let's have another look at a couple of other differences. So we'll just draw a graph of the potential difference that a voltmeter would show if it was plugged into either the terminals of a battery or the terminals of the power pack, like we've used in class, or in this case, for AC, if we were to push the ends of the wires from the voltmeter, probably a bad idea, but if we were to push them into a plug socket, into two of the holes in the plug socket, we'll come back to which two in a second. So there exists a machine called an oscilloscope, which is a box that kind of draws a graph of potential difference for you as time ticks by. So here's what an oscilloscope would draw as a graph if we attached it to a battery. So it's kind of like a fancy voltmeter. Instead of showing you a number on a screen, it draws you the graph so that you don't have to do it for yourself. And then when it runs out of screen, it whips back to the other side, to the left-hand side again, and starts drawing the graph all over again. So if we were to attach one of these fancy voltmeter graph drawing oscilloscopes to a battery or a power supply, it would just read that. The kind of batteries that we've got in our homes are generally 1.5 volts. If you've got a remote control near you, or if your mouse has got a battery in the bottom of it, if you just pull the battery out now and just have a little look at the battery, you'll see printed on the battery, it says somewhere 1.5 volts. And so it always gives 1.5 volts. There are chemical processes going on inside the battery or whatever's going on inside a power pack that push electrons to one terminal of the power supply, and that takes a certain amount of energy to do it. And that energy is 1.5 joules for every single coulomb. And then when the electrons run off around the circuit and they come back again, they've lost that 1.5 coulombs because the power supply gives them 1.5 extra joules. The battery gives them 1.5 extra joules per coulomb. So when they run around the circuit, they come back without it. The battery tops them back up with another 1.5 joules, and off around the circuit they run again to dump their energy in the light bulbs and things like that. Now, it is true that if we let this graph run for longer than about 8 seconds, or however long it is taking to go across there, if we let it for run, say, 8 days or 8 weeks, probably the graph would go down over time. You know that batteries have chemicals inside them that gradually run out, and eventually a battery goes flat. It doesn't even need to lose that much of its potential difference. Once a battery gets down to about 1.1, 1.0 volts, it's generally not very good for much anymore, and that's about when you start replacing them. They don't have to get down to 0. Okay, so that's direct current would come from a potential difference like that. It's always positive, and so it always pushes the electricity in one direction. That's direct current coming from the potential difference on the left. You'll notice that for the alternating current one, though, I've got a negative side to the battery. And you'll remember that when we did the bulb practical in class, I asked you to use lots of potential differences, 2, 4, 6, 8, 10, and then I asked you to pull the wires out of the power pack and swap them over and push them back into the power pack again. And suddenly the voltmeter starts saying -2, -4, -6, -8. And all that minus sign meant was that it was the other terminal that was now the negative one. The positives and the negatives are swapped over, and it caused the current to run in the opposite direction. So if we were to attach our fancy graph drawing oscilloscope to an alternating current, it would actually draw this graph. So as I said, a power station rotates round and round and round. It doesn't like flick from one state to another. So there's a continuous change as the power station rotates. Like I said, we'll do the details of power stations in a much future lesson. What that means is that you get this kind of shape in which it grows and grows and grows and grows in potential difference, hits a peak, and then it tumbles back down again, and then it reverses. And it goes negative, which means the current flows in the other direction because the positive and negative terminals have swapped roles. And so now it grows and grows and grows and peaks and peaks and then shrinks and shrinks and shrinks, but this time in the other direction, which means that the current is now going in the opposite direction. So here in this first little bit here, that's the electricity all traveling, say, left to right. And then it goes right to left, and then left to right, and right to left, and left to right. And this plus minus plus minus plus minus is what's creating the difference in direction. But also look that it's making a difference in the actual value of the potential difference. It's not like the battery, which remains at a constant value. This potential difference is sometimes very, very small, sometimes very, very big, then very small, then very big, then very small, then very big. Which means not only do the electrons flow in different directions, they actually flow at different kinetic energies. Because when the potential difference is very, very small, the electrons are only given a little nudge around the circuit and they move quite slowly. But then when the potential difference grows very, very big, suddenly that's a much bigger push, much more electrons involved on the terminal, and the electrons move very fast. So if you could shrink down and look inside a wire with an alternating current in it, yes, you would see the electrons moving left, right, left, right, left, right, never really seeming to go anywhere. But also you'd see them speed up, get to a very fast speed, then slow down, 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 and then they'd stop. And then they'd turn around and then speed up gradually to a very fast speed and then slow, 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 stop. So the actual size of the potential difference varies as well. It's not constant. So when you put a battery into a device and it says 1.5 volts, you're getting 1.5 volts, exactly what it says on the packet. But when you plug something into mains electricity, you are not getting a nice constant stream of electricity. It keeps going big, small, big, small, big, small. In fact, if you look at the graph on the screen in front of you, quite regularly it hits 0, which means actually anything you like that you plug in actually turns off regularly. When your light bulb is on, it's actually flashing. Now, to be fair, as we'll see in a minute, it's flashing so quickly that the human brain can't tell. And in fact, for a light bulb, it has to cool down before you'd notice the light going off. And it's flashing on and off way too fast to cool down. So you're not going to notice a light bulb flashing. And electronic devices are designed to cope with this momentary small potential difference, sometimes even 0 potential difference. But it is interesting to think that we're powering our country using a power supply that regularly actually hits 0 volts. Okay, let's just focus on this alternating current graph because there are some numbers that I want you to learn. Okay, that's the phrase that I need you to sear into your memory. As UK residents, your electricity that comes out of your plug socket is defined by those 2 numbers, 230 volts and 50 hertz. When you got your mic on? Mark, I'm just going to mute you. Oh, no, I can't. There we go. Okay, so what do those two numbers mean? Okay, let's do the 230 first. So the 230 volts isn't actually the peak. It's kind of an average value. Now, for the geeky mathematicians amongst you, you can see that if we average a whole load of positive numbers with a whole load of negative numbers that are exactly the same, when you add them all up, it's going to add up to 0. And so when you divide, you're going to get a 0 answer. The average, the mean of all of this is 0. So when I say it's a kind of average, I mean it's an average as if we treat everything positive. So if we were to take all those negative numbers under the graph and make them positive and kind of do an averaging of just the positive values, 230 would be what we come up with. We actually, because we get computers to do these averaging for us, and we just need a computer routine that can very quickly make things positive, we actually square the numbers. It's just a really quick mathematical way to make negative numbers positive. So we actually square all the numbers, take the average of the squares, and then square root the answer. So for the maths nerds, that's called a root mean square. It's a new kind of average that maybe you haven't heard of before. So you can look that up if you want to. So your mains electricity is averaging 230 volts, but it can get up as high as 315, and it's regularly 0. Definitely not constant. So fix that in your head. In the UK, the mains electricity supply averages 230 volts. In other countries, that's not the same. In America, for instance, I think it's about 115, about half of that. Possibly in Europe as well, I can't remember. So it's important to realize that these are UK numbers. And what does the 50 hertz mean? The HZ stands for hertz, which is a unit named after a scientist, as we do with units. So hertz, H-E-R-T-Z. Oh, done that. Okay, so what does the 50 hertz mean? Well, it turns out that it takes 1/50th of a second for the electrons to move all the way to the right, stop, turn around, move all the way to the left, stop, turn around, and come back to where they started from. So that means that every single second, the electrons do this kind of left, right, left, right, left, right dance 50 times in a single second. And that's what the 50 hertz means. It means that the current oscillates left and right 50 times every second. Sometimes it's referred to as a cycle. So we would say that it's 50 cycles per second. If you want to be impressed by that, it's doing that 50 times a second because the generator is spinning 50 times a second. Now, 50 times a second, well, that's fast. I mean, imagine I sit you on an office spinning chair and get your mate to spin you 50 times a second. Or even a park roundabout, you could get round, what, once in a second, twice in a second? Not 50 times a second. You'd be hard pushed to pedal your bike with the wheel going round 50 times a second. 50 times a second is really fast. And you probably don't know, why would you? But an electrical generator is about the size of a double-decker bus. So the fact that it's spinning 50 times a second, that's impressive. Other countries spin their generators slightly faster or slightly slower, but in the UK, it's 50 hertz. Right, of everything that I have so far said today, the slide that is in front of you now is the only bit that's actually examinable, that you actually need notes on. And I've placed this PowerPoint on Google Classroom. So when this lesson's over, I just need you to make a copy of that one slide into your books. That captures everything that I've said so far that you need to remember. Okay, so 230 volts. That's a little bit higher than 1.5, isn't it? In fact, what's that? I don't know, getting on for 200 times? not quite 200 times, but it's a lot bigger than a battery. This is good. It allows us to power things that require much more energy than a battery can provide. A 1.5 volt battery just about powers your remote control, or maybe a torch. If you want to power your power shower or your oven or your fridge, or an electric drill or your hairdryer or anything that guzzles energy, you're going to run out of batteries very quickly if you try and use batteries. 230 volts means 230 joules for every single coulomb of electricity that passes through the device. That's a lot more energy, and that's a lot more capable of doing more effective jobs. And all of the electrical devices in your house work the way they do, generally because they're plugged into 230 volts, not 1.5 volts, the appliances. But that brings with it our second half of our lesson. You see, the mains electricity is probably the most dangerous thing in your house. And so we're going to spend the second half of this little lesson this afternoon talking about how it is that we have put this incredibly dangerous device in our homes, and yet we're managing to live with it just fine for the most part. So let's talk a little bit about the safety implications of 230 volts. Okay, it comes down to what we call electric shocks, but what does that mean? Well, an electric shock means that we run an electric current through the human body, and that is not easy to do. The resistance of dry skin is around about 100,000 ohms. So to run an electric current through 100,000 ohms is going to take a bit of effort. If you try and do it with a 1.5 volt battery, you get a current of about 100th of a milliamp. That's nothing, is it? You don't even notice it when you touch the ends of a battery. It does run through your body. There is a tiny little current that runs through you, but it doesn't do anything to you. If you've got any 9 volt batteries, they're the kind of cuboid shaped ones that have got the terminals on the same end. If you clean it a little bit first with some wipes, we've all got wipes at the moment, and then just touch it to your tongue. Your saliva is a little bit more conductive than your dry skin, and obviously we've gone from 1.5 volts to 9 volts, and we get a slightly larger current, and it's enough to make the nerves on the end of your tongue tingle, and that's the most impressive thing you're going to be able to do to the human body with a battery. Not a car battery, by the way. They are different constructions. Car batteries are capable of doing you some damage, even though they're only 12 volts. So don't go touching a car battery. Okay, so that's why batteries are safe. But what about mains electricity? Well, if you touch the mains electricity, you're up to a current of around about 2 milliamps. Now, I hope you know from your biology that the nerves running through your body that carry signals, they carry electrical signals, and your nerves are like tiny little biological wires inside your body, and they're coated in a layer of fat. That's one of the reasons why we need to have fat in our diet, to make sure that our nerves remain insulated, otherwise they stop working properly. You can get some degenerative nerve diseases if that's the case, so you need to make sure that you have a little bit of fat in your diet. And those little biological wires, they carry currents. And if you were to touch the exposed terminals from the mains electricity, then that's enough to push around about 2 milliamps through your body. Now, you might be surprised to know that that is bigger than the currents that run through your nerves naturally. And it's certainly a much bigger signal than your motor nerves are used to. And it's enough to send a signal to your muscles that swamps any signal from your brain, and it causes your muscles to contract, which means if you're unlucky enough to have just grabbed hold of something that is live with mains electricity, the first thing that's likely to happen to you is that the electric current that the 230 volts forces down your arm is very likely to make your muscles contract. And so horrifically, you are likely to grab hold of the thing that's electrocuting you and be unable to let it go, which is not a good thing. If it passes down through your legs into the floor, it will make your leg muscles contract with more power than you are capable of voluntarily making your leg muscles contract. So much so that you are likely to do the high jump of your life and throw yourself across the room, which might sound funny, but if you land on something that's going to break bits of you, it's not going to be funny at all. If you land on glass or something pointy or just a wall, you can break your neck or something. So any of those things you've seen in films where someone touches something electrical and goes flying across the room, it's not the electricity that flew them across the room. That's not possible. It's their own muscles that threw them across the room as their leg muscles contract and just, like I say, do the best high jump ever. That's the least of your worries, muscle contractions. See, if you're stupid enough to touch something electrical using wet hands, skin has a resistance of 100,000 ohms, but wet skin, it comes down to just about 1,000 ohms, which means when you run 230 volts across you, you get a current of about 200 milliamps running through your body. Now, to put that in context, 10 milliamps really hurts a lot. Like excruciating pain hurts. And we're up to 200 milliamps now from wet hands. Another unpleasant thing about electricity is that if you are getting an electric shock, it alters the chemistry of your skin. It can actually lead to burns, which we'll talk about in a second. And actually, during an electric shock, even dry skin can have its resistance brought down to about 500 ohms, which is up to 500 milliamps now, half an amp. So moving back through the list, 10 milliamps hurts, 20 milliamps pushes enough energy through your body to give you serious burns. I mean, hospitalization serious burns, as if you just put your hand in a Bunsen burner flame. From 20 milliamps, well, that's still a tenth of 230 milliamps. In fact, 200 milliamps will stop your heart. You have nerves causing your heart muscle to contract, and up at that kind of currents, it will completely swamp the currents that are causing your heart to beat, and it'll stop your heart. And unlike the films where, you know, people do CPR for a bit and then the hero or the heroine sits up and goes, "Oh, thanks very much for saving my life." It's not like that in real life. CPR is something we do until an ambulance arrives with a defibrillator, which provides a much carefully targeted electric current to restart the heart again. So electric shocks, which basically means an electric current being pushed through the human body, we have to worry about those when we move from 1.5 volts to 230 volts, because the current becomes high enough to do serious damage to the human body. Okay, we have some lines of defense, and the first and the foremost is that we teach our children when they are very, very young, do not touch the plug socket, do not play with electricity, do not chew the electrical cable, and certainly do not turn the light switches on and off when your hands are wet. So you learnt that from you know, the age of 1 or 2. Do not play with electricity, and that's just built into us. And so we are generally very safe with electricity. Parents do a really good job of teaching their kids about electrical safety. But even then, we need a little bit of a helping hand, because there's no guarding against stupidity or absent-mindedness. So I want to talk about 2 things that are deliberately manufactured into electrical devices to keep us safe around them. The first is the construction of the devices themselves, in particular the plugs and the wires, and we're going to do that now. And then there is a particular safety feature called the fuse and the earth wire, the 2 go together. And we're going to talk about those next lesson. They're a bit more complicated. Okay, so let's talk about the plugs and the wires. Okay, so I don't know how much you've ever really examined a plug or a wire beyond sticking it into the wall, but you're supposed to know some stuff and be able to describe it. So, for instance, you should be able to say that plugs are made out of plastic because plastic's an insulator. Cables are also made out of plastic, on the outside at least, because plastic's an insulator. It means we can touch it and handle it, and we're not going to get electrocuted. The electricity can't pass through it. But we use bendy plastic. Oops, wrong one. Bendy plastic for the cables because we're always coiling them up or running them around corners. But we want hard, durable plastic for the plugs because we're constantly picking them up and pushing them in and pulling them out, pushing them in, and then we walk around and bang them into things as we're dragging them around the house behind us. So tough, durable plastic for the plug and bendy plastic for the cable. Then let's talk about the conducting bit. So we've got this copper wire here. We use copper because it's reasonably affordable. It's not cheap, but it's cheaper than other things. It's a pretty good conductor. It's quite bendy, which means we can coil the wire up into different places, bend it around things. For thin bits of copper, we often break it into multiple strands, like in this picture, but for thicker pieces, we just leave it as one big chunk. And then we actually need three lots of copper in every cable. We'll come to why in a second, which means there's a second line of plastic inside the wire, wrapping each wire separately so they're kept apart and the currents don't jump from one to the other. And we color code them so we know which wire is which. So copper's great, good conductor, reasonably cheap, pretty bendy. But we want the same properties for the plug without the bendy bit. So the pins are actually made of brass, which is an alloy of copper. That means we've mixed the copper with other metals to make it a little bit stronger. This means that when we push the pins in and out of the plug socket, they don't bend. So copper, my mouse is playing up, copper and brass. A couple of other little safety features. This pin here is safer than the other two. These are kind of like the terminals of the power pack. These are the dangerous ones. We'll come to that in a second, but this one isn't. This one's reasonably safe. And whether you know already because you've plugged things in before or because you can see it from this picture, this pin's slightly longer than the other two pins. And what that means is that that pin goes into the plug socket first, before the other two pins do, and that triggers some safety features inside the plug socket. So for instance, there's a little trapdoor mechanism inside the plug socket. So when the top pin goes in, it opens up some little protective plastic openings on the bottom two pins to allow those two in. Also, the top pin kind of provides a level of safety, which we'll come to next lesson. And so that engages before the other two pins engage with whatever's inside the plug socket. And that means that the safety feature is switched on before the rest of the plug. Also notice the plastic that's been wrapped around these bottom two pins. The end of the pins have been left exposed, but the bits that aren't actually going to do any connecting to anything have been wrapped in plastic. And that's so that if you've got little fingers, like when you're a tiny little kid, if you're plugging a plug in, you might accidentally reach your fingers around the back of the plug between the plug and the socket. And you might actually be touching one of those pins as it pushes into the plug socket. Well, you can only touch the plastic bits because by the time the pins hit anything dangerous inside the plug socket, it's only the plastic bit that's left sticking out into the world. So just subtle little safety features to keep us safe. It's surprising perhaps to think about just how engineered a plug is with safety features. Okay, let's have a little look inside the plug and follow the story. So these cables, or these wires inside the cable, they need connecting inside that plug. So this little screw here needs to be unscrewed, and inside the plug is this. Okay, I need you to listen very, very carefully to the next couple of sentences. If we were in class, I would be giving you plugs, and I would be giving you screwdrivers and cables, and I'd be letting you wire up some plugs. And you could have a go at actually attaching the cable to the plug. I reckon I wire a plug up about half a dozen times a year, even if it's just silly things like taking a plug off a cable so that I can thread it behind a piece of furniture because the cable fits, but the plug doesn't. And then when I fish it back out the other side of the piece of furniture that I've run it behind, I put the plug back on. Or maybe I broke the plug. I have this habit of dropping the plug from the iron on my kitchen floor, which is really hard, and I keep smashing the plug. My wife's not very happy about it, so I have to keep replacing the plug on that. It's surprising how often you find yourself attaching a plug to a device in your house. And so it's good to practice it. You must not practice it. You're not with me at school. I'm not there to supervise you. You don't get to wire plugs at home unless there is an adult in your house who knows how to wire a plug and is willing to sit with you and teach you how to do it and check that it's safe after you've finished it. Because if you miswire a plug, if you do it wrong and then you plug it in, you can get electrocuted. Or the next person to use the lamp or whatever it is you just rewired can get electrocuted. So I want to be crystal clear on this point. When this lesson finishes, you are not under any circumstances to go and find yourself a plug and a screwdriver and start rewiring a plug. However, it's a really good activity. So if there is an adult who knows how to do it, who'd be willing to show you, then that would be a really good activity for you to do at home. But you must not do it on your own. It's not safe that you might not do it right, and then the device will be dangerous afterwards. So don't do it yourself. Okay, hopefully you've listened to that. Okay, this is what a correctly wired plug looks like inside. I'm going to leave you with some activities to do and some reading to do, so I'm just going to quickly go over this. You must make sure that the colors are connected to the right screws. This is the back of the plug, and this bit is the back of the top pin, and this is the back of the side pin, and this is the back of the other pin. There's a little bit in between here called the fuse, which we'll come to next lesson. So you must make sure that the brown wire is connected to the correct pin, the blue wire is connected to the correct pin, and this stripy wire, which is kind of supposed to remind you of kind of hazard tape or something like that, this is connected to the top pin. And you can't muddle them up, because at the other end of the wire, it's connected to a TV or a lamp or a radio or something. And those wires are connected to particular parts of the device. And it won't work properly if you connect up the plug end wrong. So you just need to make sure that you learn off by heart which colors go where. And there's a little video that I'm going to ask you to watch later, which has a nice little way of reminding you which color goes in which plug. Okay, the brown wire is referred to as the live wire. It's the one with the 230 volts. It's the one that will kill you. It's the one you must never touch, and it's the one that's got this safety feature attached to it. My good old dad, thanks Dad, once gave me this great advice, which I shall never forget, and I'm going to foist it upon you so that you may know my pain. He told me once that the brown wire is the live wire, and the way to remember that is because brown is the color my trousers will go if I touch it. Thanks, Dad. But he's right. I never have forgotten that, so maybe I do need a genuine thanks. Blue is the neutral wire. It's the 0 volts wire. It's the one that the electricity is returning to the power station through without any energy left in it. It is usually around about 0 volts, depending on how far you live from the power station. It can be a little bit higher. We'll come to that another day. But generally, it should be safe, but you can't trust it, so don't touch that one either. But blue is supposed to remind you of cold. It's got no energy left inside it. The brown wire and the blue wire are the business wires. They're the thing that do stuff. And in some circumstances, some plugs only have 2 pins and 2 wires. because only the blue and the brown are actually required. The stripy wire is a safety feature that works in conjunction with the fuse. And so it's not technically necessary, but it's a very good idea to have it. So we'll talk about the earth wire on a different lesson. So don't worry too much about what the live wire and what the fuse do right now. What I want you to focus on is which color goes in which hole. Also notice the general neatness of things. There's not much space inside a plug, so you need these wires to be the right length because there's nowhere to coil it up, any excess wire. Also, the top of the plug sits pretty flush on top of this part of the plug. So you'll notice that, you need to thread the wires into these spaces, because if one of the wires was over here, when you try and put the lid back on, it's not going to fit. And then if you were to trip over a cable and hoik some of these wires out of the plug, out of the holders that they're in, you could end up with, live wires flapping around all over the place. So there's this cable grip here, which literally grips the cable, not the wires, the cable, this little white bit sticking all the way through the cable grip. And that's making sure that if anyone trips over the cable, they're not going to accidentally pull any wires out of the plug. So the second piece of notes that you need from today's lesson, the second thing I need you to write down, is a picture of a correctly wired plug. So again, you can copy it from this slide after the lesson's over. I would like you to read this website. It's a DIY website for adults, but it's got some really lovely cartoon pictures about how to wire a plug in step by step all the way through. So also have a little look at this website so that should you ever get an opportunity to wire a plug, you can do so. But please, one more time, don't you dare start wiring plugs in your house without adult supervision. Okay, last slide, I think. I would also like you to watch this video, please. It's only 3 minutes long, but it talks you through some of the other electrical safety things, gives you a nice little thing about how to remember which wire goes where. And it's just a little bit of not me talking. So have a little watch of this video as well, 3 minutes. And then finally, if you get any chance, any time left after that, have a read through this PDF. It's attached to the classroom post. And here's a little picture of the correctly wired plug that you could copy into your book if you want to. So just to be crystal clear, there's only two things that actually need writing in your books: the graph of the 230 volts, 50 hertz slide, and what a picture of a correctly wired plug looks like. If you happen to want to do so, there are some questions here that you could try your luck at, but some of them refer to earth wires and fuses, and we haven't done that yet. We're going to do that next lesson, so you might want to hold off.